Welcome to the very first video of the HSC chemistry course. We hope you guys are as excited as us to tackle this journey that is the HSC. I know you're all probably itching to get started, so make sure you're in a comfortable spot that's not your bed, your laptop's fully charged, and you've got plenty of colored pens to follow along as we tackle this chemistry course together. Without further ado, let's get stuck into it. So the very first module that we're going to look at is the equilibrium module. And in the equilibrium module, this very first section, we're going to get introduced to what equilibrium is all about. And then in later sections, we're going to look at whether a system or a chemical reaction will reach equilibrium. And then towards the end of the module, we'll look at some calculation questions and do a bit of quantitative analysis. Okay? So with equilibrium, what exactly is equilibrium? Well, let's sort of have a look. So in year 11 chemistry, you would have looked at chemical reactions, and chemical reactions can be very, very simple, or they can be very, very complicated, right? But as a sort of generic chemical equation, you might have seen, well, we might have A plus B giving you AB, like so, right? And that was a synthesis reaction, right? But you're essentially getting one element reacting to another, and then you get a new element, right? And so that's what we're used to, and we're used to having sort of a forward-facing arrow like that. But what can also happen, given the right conditions, is we can get AB breaking down to form A plus B, like so, okay? So just as much as you can have A combining together with B to form a new molecule AB, you can have this new molecule breaking down to form its individual elements, like so. And if we combine these two equations together, right, like so, we get A plus B combining to form AB, right? But then also that product can break down to form its reactants again. And we draw this sort of symbol here, which looks a little bit like a city rail sign, right? The old city rail logo, right? But that essentially shows us that this reaction is in fact in equilibrium, meaning you have a forward reaction, but you also have a reverse reaction, right? So you have a forward reaction and you also have a reverse reaction, okay? And so that's essentially what equilibrium is, right? You have a few reactants combining together to form a couple of products, and those products are also at the same time breaking down to form those reactants again, and you're sort of cycling through that, okay? And how do we know it's an equilibrium? Well, we see this sign here, which looks like a city rail sign, meaning there's a forward reaction and a reverse reaction. And we'll talk more about this as we sort of go along, okay? Now, let's just take a step back and talk about, well, what are non-reversible reactions, right? Well, and by definition, non-reversible reactions are essentially reactions that never reach equilibrium, meaning you go from your reactants and you just form products and that's it, right? And actually, this is not necessarily true. We'll talk about this later on in this section, but pretty much all reactions are reversible given the right conditions. It's just sometimes in real life, it's really hard to get those conditions, so we just call them non-reversible. So what we mean by that is the classic example of a non-reversible reaction is essentially a combustion reaction. And if we think back to year 11, what's a combustion reaction? Well, combustion reaction is anytime you have fuel, most of the time it's in liquid, but sometimes it can be gas, reacting with oxygen to go and form carbon dioxide and water. And this is a complete combustion reaction, right? Incomplete, you get carbon monoxide and carbon, but anytime you get carbon dioxide and water as a liquid, that is a complete combustion reaction. And this is a classic sort of non-reversible reaction, or a classic example we use of a non-reversible reaction, because 99% of the time, even 100% of the time, you will see fuel burning in oxygen to create carbon dioxide and water. Very, very rarely, if ever, do you see carbon dioxide and water reacting together to form oxygen and fuel. Okay, so it rarely, if ever, goes back the other way. So this is why we call this a non-reversible reaction. It only goes forwards, right? And that's absolutely true, right? But for some reactions, they don't go to completion, meaning not all the reactants go and form products, right? And they actually do form reversible reactions. They can go both ways. And the classic example of something like this could be the Haber process. And you'll get to know the Haber process really, really well throughout, HSC chemistry. But what the Haber process essentially is, it's taking nitrogen gas like so, and reacting with hydrogen gas to form ammonia, which is this molecule here, NH3, right? And they're all gas. And just to balance this equation, we've got a 3 in front of here and then a 2 in front of here, okay? And how do we know it's reversible? Well, we again see this sort of city rail sign occurring again, meaning that the nitrogen gas will react with the hydrogen gas to form ammonia, And in the same system, ammonia is going to break down to form hydrogen and nitrogen. So both these processes are going on at the same time. You have the formation of ammonia from nitrogen and hydrogen, and then you have the breakdown of ammonia into hydrogen and nitrogen. And this sort of goes around and around and around. Okay, and you're going to reach a point where those rates are going to equal each other, right? But the key is with reversible reactions, you can go forwards and then you can go backwards. Okay, that's the main takeaway so far. All right. Now, how do we sort of map this out on a energy profile diagram, linking it to some of the stuff that we may have come across in year 11? Well, let's just use the example of the Haber process, right? Like we said, it's nitrogen reacting with hydrogen, like so, to form ammonia, NH3, like so, yeah? And so we said, well, this is the Haber process. The Haber process, the enthalpy change for it is negative, meaning it's an exothermic reaction, right? If we sort of a bit of revision from year 11 already, negative exothermic reaction, which means it's going to release energy. And if hopefully you haven't forgotten too much, we can draw an energy diagram for an exothermic reaction that might look something like this. So on the y-axis, we have energy over time. So then you're going to start with a particular energy level for a reactant. It's going to go over this hump like so, and then come back down, and you're going to end at a lower energy level for your products because you're releasing energy overall, right? So this is the energy for our reactants, and this is the energy level for our products, for example, okay? And so what's essentially happening in a reversible reaction is, well, obviously you have the forward reaction. So you have the nitrogen colliding with the hydrogen to form ammonia. And then the collision of the nitrogen and hydrogen is essentially going to overcome that activation energy there. All right, so that's the activation energy of our forward reaction. So you have the reactants overcoming that activation energy by colliding, so the nitrogen and hydrogen, and then going to form ammonia. But then also the ammonia particles are actually themselves, because you're creating these products, those ammonia particles are themselves colliding into each other. And when the ammonia particles collide with each other, they actually generate enough energy to overcome the reverse activation energy, to overcome this reverse hump here, like so. Okay, and so that's why you have a reversible reaction. You have the forward reaction where the nitrogen is colliding with the hydrogen to form ammonia. And then the ammonia particles that get formed, they're colliding with each other to overcome the reverse reaction's activation energy. And then they're going to break down and form nitrogen and hydrogen like so. Okay, so that's how we link something that we've talked about in year 11 to now a new concept that we've just talked about, which is reversible reactions, and how we can sort of show this on an energy profile diagram. Okay, right, so just to sort of clarify, on our reactants here, these are what we're talking about with our reactants, it's hydrogen and nitrogen. And then on our product side, we're talking about the ammonia, like so, okay? And these things, like we said, these are things that are colliding together to form ammonia, and the ammonia breaking down to form hydrogen and nitrogen, like so, okay? Now, the next thing that we're going to talk about is the difference between dynamic and static equilibrium. And the key is that all reversible reactions, they reach a state which we call equilibrium, okay? Because it's the most stable state. Everything in chemistry, the rule is always everything wants to go to the most stable state as possible. And for reversible reactions, the most stable state we call equilibrium, okay? So the most stable state we call equilibrium. Now, there are two types of equilibrium, right? Static and dynamic equilibrium, right? So if we divide equilibrium up, okay? If we divide equilibrium up, we said there's two types of equilibrium. The first one is a dynamic equilibrium, and the second one is a static equilibrium, okay? Now, we're going to first talk about dynamic equilibrium, because if you can understand dynamic equilibrium, you probably understand static equilibrium, because understanding dynamic equilibrium is actually a little bit harder, okay? But essentially, what's happening with, say, for example, a dynamic equilibrium is, I like to think of it using the analogy of essentially like a treadmill. So if I draw a treadmill like so, okay, so this is a treadmill like so on a side view, and then obviously you're going to be running. I'll probably be walking on the treadmill, right? But hopefully you guys will be running on the treadmill. And so, you know, you're going to be on the treadmill like so, and you're drawing a smiley face, right? Very rarely do I see people smiling on the treadmill, but that's a different story, right? So you've got someone on a treadmill here, right? And essentially, when we talk about our reversible reactions, we said there's a forward and there's a reverse reaction, okay? There's a forward and there's a reverse reaction. And essentially, the forward reaction in this analogy here would be essentially you moving forward on the treadmill, right? You're walking forward on the treadmill, but if the treadmill is not on, right, you're probably going to walk into that, you know, piece of equipment at the end here pretty quickly, right? So that's essentially our forward reaction. But then to sort of balance that forward reaction, we have a reverse reaction. And the reverse reaction is essentially that sort of treadmill belt that's going the opposite direction, right? And so forward reaction is us moving forward, the reverse reaction is the treadmill moving backwards. So then how does this relate to this concept of equilibrium? Well, we define equilibrium, and we'll talk about sort of dynamic equilibrium specifically in a sec. We define equilibrium in general as the situation in which the forward rate of reaction equals the reverse rate of reaction, okay? So what's going to happen is when you first get on a treadmill, you might be trying to adjust your speed, you might be running too quickly, right? And then you might slow it down, or you might increase the speed of the belt, right? And then hopefully you'll adjust your running speed and you'll adjust the speed of the belt to a point where they both balance each other out, where you're running at a particular pace that you're able to maintain and the belt's moving at a particular pace that it's able to maintain, such that you as the person on the treadmill don't change, right? You're standing in the same spot. Even though you're sort of running and the treadmill is moving, you're staying in the same spot. And essentially what you've done is you've achieved what we call dynamic equilibrium, where you have a positive forward reaction, so you're still running forward, right? And you have a positive reverse reaction, so that the treadmill is still walking, but there's no change in concentration, or you're not moving spots. There's no change in concentration. Okay, so that's essentially what a dynamic equilibrium is. You have the forward rate equaling the reverse rate, such that there's no change in concentration, right? But the key is the forward rate equals the reverse rate. Okay, the forward rate equals the reverse rate. Okay, such that there's no change in concentration. Right? And this is what we call a dynamic process, right? What we mean by a dynamic process is the forward reaction is occurring and the reverse reaction is occurring. And if we compare that to now a static equilibrium, now draw the same thing, right? Draw a treadmill. A static equilibrium is essentially you're just standing still on the treadmill like so. You're not running at all, right? So that's what we call a static equilibrium. Right? It's still equilibrium because your forward rate is equal to your reverse rate and there's no change in concentration. So you're still in the same spot on the treadmill, there's no change in concentration, but the forward and reverse rate are equal to 0, okay? So with a static equilibrium, the forward and reverse rate are equal to 0. Essentially, you've got nothing going on. And that's not very common in chemistry. So the main equilibrium that we're going to be talking about in chemistry when we refer to equilibrium is a dynamic equilibrium, okay? Now, what does this sort of look like on a graph? So this is sort of the analogy of it, but what does this actually look like on a graph? Well, if we try to map out a dynamic and a static equilibrium, well, with a dynamic equilibrium, right? Dynamic equilibrium, well, we said dynamic equilibrium or equilibrium is any time your forward rate equals your reverse rate, such that the concentration isn't going to change, right? So if we have a look at our dynamic equilibrium, right, let's just go with the equation A plus B going towards AB like so, and then AB is going to break down, etc. If we label this axis our rate of reaction, okay, if this is our rate of reaction, all right, essentially over time, right, over time, what's going to happen is when we first start off, let's just say we start off with only reactants, right? If we only start off with our reactants, what's going to happen is the rate of reaction is going to occur really, really quickly, right? You're going to get this rush of this forward reaction, right? Because you just mix the reactants together, they're going to form the products really, really quickly. So you get this rush, that's why you start really, really high. And then what's going to happen is as you start to convert some of those reactants to products, right, it's going to slow down a little bit. Yeah, so you get this huge surge, right? Because everyone's really excited. All the particles have just found each other. It's like kind of like seeing your friend that you haven't seen in a while. There's so much to talk about. You're really, really excited. So the rate of reaction is really, really quick. But then as sort of time progresses, it starts to slow down and it starts to taper off, okay? As you're converting more of your reactants to your products, okay? Now, what's going to happen on the product side is, well, we're going to start really low because there's not that much product present. But then as your reactants convert to more products, then there's going to be more products present. And when there's more products present, they're going to collide with each other and then form our reactants again. So what's going to happen with that on the product side is you're going to get this initially start really low and then you're going to sort of taper off and then meet at the same point like so. Okay, now there's a couple of things to label in, right? The blue line, that's essentially going from A plus B to form AB, and then that red line here is going from AB back down to A plus B like so, okay? And then where they meet each other and where they become equal, that's what we call our equilibrium point, right? That's our equilibrium point, because remember we defined equilibrium as essentially the rate of the forward reaction equaling the rate of the reverse reaction. And essentially what we've seen here is we see the forward reaction, this blue line here, has now equaled the rate of the reverse reaction, this red line here. So now you're at equilibrium. These points are equal, right? And so you're at equilibrium, and there's no change in concentration because the forward and the reverse reaction, the key thing to note is that they're still positive, right? The forward and the reverse rate of reaction, it's still positive, but when you're combining A and B to form AB, when you're making the product, well, the AB particles or your products are going to break down at the same rate to create your reactants. So the reactants are forming products at the same rate that the products are breaking down to form reactants. So that's why at this point, there's therefore no change. This triangle means change, no change in concentration. Okay, so that's why there's no change in concentration, because there's still something going on. That's why it's a dynamic process, right? This is why it's a dynamic process. Still something going on. Your reactants are going to form your products, but at the same rate, your products are going and breaking down to form your reactants. Okay. Now, for static equilibrium, it's actually a lot easier, right? So what was the difference between static and dynamic equilibrium? Well, we said for static equilibrium, right? So we said for static equilibrium, we said it's when your forward and reverse rate of reactions equal each other, which is fine, right? Because that's what an equilibrium is, right? But it's at zero, it's equal to zero. So there's nothing going on. So it's really easy to draw this because we just draw it as a line at zero, okay? i.e. your forward and your reverse rate equals zero, okay? i.e. your forward equals your reverse rate of reaction, okay? Which essentially equals zero. Nothing's going on. And this happens either because you haven't started the reaction yet, so there's nothing going on, none of the reactants have mixed together, so there's no action yet, or you finish the reaction, okay? You finish the reaction where all the action's over. So essentially you have no forward or reverse rate of reaction. Okay, so either haven't started, either haven't finished, right? And that's the sort of the main situations where you get a static equilibrium in chemistry, okay? In physics, you get static equilibriums in other situations relating to forces and stuff like that, but we won't go into that, okay? Now, how do we represent it in a diagram? And this is actually quite a common exam question. It's actually come up in a few school trial papers, right? So essentially with a diagrammatic representation of equilibrium, not so much looking at specific chemical reactions, but just understanding what the concept of an equilibrium is. Let's just go with the same example where you have maybe a red molecule reacting with a blue molecule, right? Reacting with a blue molecule to then form sort of a red and blue molecule like so. Red and blue molecule like so, okay? Now, if we were to draw in a static and a dynamic equilibrium, see what they look like. Well, let's just draw the dynamic on the left-hand side here, and let's just draw the static on the right-hand side here, like so. And we'll start off with the static, because that one's the easy one to draw. So we said static occurs anytime you either haven't started the reaction or you finished the reaction. So let's just go with you haven't started the reaction, right? And so essentially, you might have maybe these sort of red particles present, right? And these are your red atoms, and then these are your blue atoms, right? Like so. And the key thing here is that none of them have mixed together, none of them has started reacting, right? So there's no sort of rate of reaction. The forward and reverse rate of reaction are equal because they're zero, right? And so that's what a static equilibrium is. Now, if I just sort of replicate this, like so, okay? So if I just replicate that and show what a dynamic process is, well, a dynamic process, we said there is something going on, right? There is a forward reaction and there is a reverse reaction, right? But there's no change in concentration, right? So this is at the very, very start, right? So we're not at equilibrium yet. And so the equation might move towards equilibrium, right? So the equation might move towards equilibrium. So what that means is maybe some of these red particles will then come and then form some of these blue particles, and that will combine into one, right? And then maybe these will combine together like so, and then maybe these will combine together like so, okay? Now, we're probably getting closer and closer to equilibrium because the forward reaction is progressing, right? And then what happens is, well, now that we've formed some of these products, right? So we said that we have the forward reaction going where the red is reacting with the blue to form this this sort of red and blue molecule here, right? So that's absolutely going on. But then what happens is once we start to form those products, these products might then decide, okay, well, I don't really like this person anymore. I wanna split apart, right? And so what can it do there? Well, then just as we're creating our products, right? These products might be breaking apart like so. So that might break apart like so, right? So that one of them might break apart. And then these ones here might go and form a molecule like that, right? And then, well, these ones here, that might break apart, right? So this one here, that might break apart. Now, if you sort of go and then if you sort of continue this process and then count how much is present, well, these ones might combine together like so, right? These ones might combine together like so, right? And then, these ones here might break apart, right? These ones here might break apart. And if you notice, right, and then one more, we'll do one more just for example's sake, these might combine together. If you notice, we still have our 3 products, and then we still have, our 4, whatever, or two lots of 2 reactants, right? I might just draw one more, so it's like sort of even Stevens, right? I might draw one more like that, right? Essentially got 3 pairs of your reactants and then 3 molecules of your product, right? And it's constantly going to stay like that, even though things are rearranging themselves, right? So this might split up again, and then these ones might form like so, right? And then, I don't know, maybe these ones, and then maybe these ones might split up like that, and then these ones might form, right? So it's a dynamic process, but you still end up with the same amount of each of them, right? You still end up with the same amount of each of them. And that's essentially what a dynamic process is, all right? Or a dynamic equilibrium. You have the forward equaling the reverse rate of reaction. So just as the reactants are combining to form the product is then breaking down to form our reactants, right? And it's happening at a rate such that the concentration overall of our reactants and products aren't changing. But it's a dynamic process because there's something always going on. It just doesn't look like it because the forward rate and the reverse rate are canceling each other out. Okay, that's how we essentially draw a dynamic equilibrium. Obviously, in an exam, you wouldn't be able to show that they're sort of reforming and breaking down. All you just have to be able to do is to show that there are some products and there are some reactants present, right? Because at equilibrium, you have both the reactants and the products present, and then you would then be asked to sort of explain that process there. Okay, the difference between a dynamic and a static equilibrium. Okay. All right, so that's understanding dynamic and static equilibrium. Then next concept is to look at sort of the difference between an open and a closed system. And an open and a closed system, the names can be sort of quite self-explanatory. With an open system, that means you're able to interact with the surrounding environment. So the open system, you're able to interact with the surrounding environment, and the closed system, you're not able to interact. So the example I like to use, or the analogy I like to use, is essentially think of it as a saucepan. So if we think of it as a saucepan like so, okay, like if that's what a saucepan kind of looks like, hopefully, right? What happens is, think of like whatever you're cooking in here as your chemical reaction, right? So if we think about whatever's cooking in here, what can happen is essentially, if you have an open system, what can happen is essentially the heat can escape, right? So that's open system. The system or the reaction is able to interact with the rest of the environment, right? The system or the reaction is able to interact with the rest of the environment. But now if I close this system, and we can close this system by essentially putting a lid on, when we close the system, then the heat's going to get trapped in here, right? It's going to get trapped and it can't escape. And that's essentially what we call a closed system, where you're not able to interact with the surrounding environment. And this is a sort of important concept for the next section when we talk about, but it's just an important concept to understand in general, where in your system, right, if we call this, if you just call this Bossack system, this is where your reaction occurs, right? This is where your reaction occurs. And then everything outside the system, we call our surroundings, or we call our environment, okay? And you need to sort of treat the reaction and the surroundings as two separate things. If it's an open system, it means the reaction and the surroundings can interact with each other, right? So you can get maybe like heat transfer, or you can get concentration increases or pressure changes and stuff like that. But if it's a closed system, it means the reaction cannot react with the surroundings, okay? And this is important because of this concept here, which is essentially dynamic equilibriums can only occur in closed systems, okay? So we can only reach equilibrium when we're in a closed system. Static, it doesn't matter, right? But we don't talk much about static in chemistry, so we don't worry too much about that. But we talk a lot about dynamic equilibrium. And dynamic equilibrium can only occur in closed systems where the reaction is not interacting with our surroundings. In the next section, we'll talk about what actually happens to equilibrium if we suddenly open it up to the rest of the environment, okay? What happens if we temporarily open up a system at equilibrium to the rest of the environment, seeing what happens then, okay, to the reaction. But the key takeaway here is that dynamic equilibriums only occur in closed systems, okay? So then just sort of to recap what we've talked about so far, right? We talked about initially what in the world is an equilibrium reaction. It's actually not too different from the normal chemical reactions that we've seen. Instead of just going in one direction, it's sort of a bit more adaptable. We can go in two directions, okay? So equilibrium reactions or reversible reactions can go in two directions. There's a forward and a reverse reaction, right? And we talked about it in terms of our energy profile diagrams. It's essentially just overcoming activation energies, being able to do that for both the forward and the reverse reaction. And then we talked about the difference between a dynamic and static equilibrium, and that is a very common exam question that they'll ask you to distinguish between a dynamic and a static equilibrium. Equilibrium is anytime your forward and reverse rate of reaction are equal. Dynamic just means that that rate is greater than zero, so there's always something going on, whereas static, nothing's going on, so the forward and the reverse rate are equal to zero, okay? we'll be able to draw it on a graph, so be able to draw it on a graph and then be able to represent it sort of in a diagram, all right? And then the final thing we talked about is the difference between an open and closed system. For a dynamic equilibrium to actually reach equilibrium, it has to be in a closed system, okay?